Quantities and units are not the most exciting way to start a physics course, but they're necessary, so let's get into it. A quantity is anything we can measure, such as mass or length or time, and a unit is how we measure it. Now, in everyday life, we sometimes leave out units if they're obvious. For example, if I say my height is 187, you'll probably assume that I'm talking about centimetres. But in physics, every answer must have a unit, even if it's obvious. In the West, it's custom to write quantity equals value unit, such as force equals 12 newtons. Sometimes my students in Taiwan will write something like 12 equals F. Now, which way around it goes shouldn't really matter, but writing it like that often doesn't have a unit, and therefore I recommend getting in the habit of writing force equals 12 newtons. Humans have been measuring for a very long time. Here's a bronze ruler from the Han Dynasty over 2,000 years ago. In Europe, units were often based on their kings, but then when the king died or changed, the units needed to change, and that was impractical. So when the French held their revolution and overthrew their royal family, they also decided to bring in a more sensible unit system, which gradually became the metric system and what we know today as SI units, which I'm going to call the System of International Units since I can't say the French. SI units were officially adopted by the world in 1971, but adopting them for a country is a gradual process. And contrary to popular belief, the United States actually follows the metric system. It was officially adopted as the preferred system of trade and commerce in 1988. However, we might say that Americans are somewhat behind much of the rest of the world in using SI units in daily life. So there are many road signs, for example, still in miles. And because of that, many AP textbooks have questions about converting, for example, between miles and kilometres. I usually don't recommend those questions to students who aren't American. In AP Physics, we mostly look at 3 units, the second, the metre and the kilogram. Then in Physics 2, we include the ampere and the Kelvin. Anyone who studied any chemistry will already be familiar with the mole, and the candela doesn't usually come up much in high school physics. The metre was originally chosen to be 1/10,000,000th of the Earth's quadrant. That is the distance from the equator to the North Pole through Pallas. And when I teach this to my students, I ask them to calculate what 1/10,000,000th of the Earth's quadrant would be if the Earth was perfectly spherical. Now, it's not perfectly spherical, and measurement has improved since the time of the French Revolution, but it usually comes out pretty close to 1 metre. Nowadays, a metre is defined in terms of the speed of light. Perhaps the most obvious period of time is the day, the time it takes the Earth to rotate once on its axis. It was long ago divided up into 24 hours, 60 minutes, and 60 seconds, and for a long time, that was what a second was. However, the Earth is actually slowing down very slightly in its rotation, and therefore a second has been redefined in terms of quantum physics principles. So occasionally a leap second needs to be added in order to keep our clocks synchronized with night and day. However, we won't notice it in daily life. The kilogram is a slightly more complicated unit. An easy way to visualize a kilogram, and also a useful way to measure it in a laboratory or perhaps a kitchen, is that it has a very similar mass to 1 litre of water, 10 centimetres by 10 centimetres by 10 centimetres. However, the density of water depends on temperature and air pressure and is also affected by impurities, so it's not a reliable enough way to define a kilogram. Until 2019, the kilogram was defined as what we call a lump of stuff measurement. That is, a kilogram was officially defined as the mass of a lump of stuff in France. Nowadays, it's defined in terms of fundamental constants of nature. However, I just want to talk a little more about what that means. If you were to, for example, go down to your local market and buy a kilogram of bananas, get home and find it was only 990 grams, sue them, and appeal it to the highest court in the land, eventually the ultimate way to determine whether or not you had a kilogram of bananas would be to pop them on scales, take that official kilogram and see if they weighed the same. If you've studied some physics before, you might be thinking, but what about all those other units I studied? Newtons and joules and watts. Aren't they SI units? And indeed they are. But they're what we call derived units, meaning they are derived from the base units we've looked at so far. Let's look at a middle school example that everyone's familiar with, speed. Now we know the formula for speed is distance over time. So, speed is in fact a measurement of the dimension of length divided by the dimension of time. Therefore, its units are the unit of length divided by the unit of time, meters per second. Now let's look at acceleration. Acceleration is speed over time, so its units are meters per second, or meters per second squared. Now let's multiply it by mass and get force. We know force is mass times acceleration, so its units are kilogram meters per second squared. But you've probably learned that force is measured in newtons. What that tells us is that a newton is a kilogram meter per second squared. It's just a special name in honour of Isaac Newton, or another way to think of it is a newton is the force required to accelerate 1 kilogram at 1 meter per second squared. And work we know is force times distance, so its units are kg meters squared per second squared, and that is a joule. So a joule is just 1 kilogram meter squared per second squared. Now, if in a physics exam you forget the unit for work, hopefully you won't, but it's generally okay to write kg meter squared per second squared if you forget the joule. And you can work that out just from the formula as we've done now. Dimensional analysis is actually very useful in deriving equations, which is an important skill in AP Physics. Now, you'll derive your own equations, but for an example, let's just use the kinematics formula straight from the equation sheet, x equals x0 plus v0 t plus a half at squared. Now, the rule for dimensional analysis is everything in between plus, minus, or equal signs must have the same basic units. The x is measured in meters, x0 of course is also measured in meters, vx, the speed, is meters per second, times second is meters, and then a half at squared, meters per second squared, times second squared is again meters. So that gives us m equals m plus m plus m. That may not seem very enlightening, but it basically confirms that this equation is dimensionally consistent. It doesn't necessarily mean that it's correct. For example, if we'd not included the half when we derived the formula, perhaps we forgot that we've got an area under a graph and we left off the half, it would still be dimensionally correct. But if you check an equation and you get something like m equals m plus ms, then you know that something is wrong in that derivation. And I recommend checking your equations as you go for that reason. SI units are closely connected with the metric system. If we're doing a calculation which involves derived units, such as newtons or joules, we must convert to the base SI units. The reason for that is because a newton is the force required to accelerate 1 kilogram by 1 meter per second squared. So in order to give a force in newtons, we have to have converted the mass to kilograms, length involved to meters, and time to seconds. Most people know the metric system, it's given to us in the exam here, but let's do a few silly conversions. 10 to the 6 phones is, of course, a megaphone. And the other side, 10 to the minus 6 phones, is, of course, a microphone. 10 cards is 1 deca cards. Now, deca just means 10. It's not so commonly used, and it's not used in AP, but you might come across it. 10 to the minus 6 fish is a microfish. Not many people use microfish nowadays, but it was basically an analog data storage system. These ones are a little harder. Please try and work them out yourself. 10 to the minus 2 mental is 1 centimental. 10 to the minus 12 boos is a peekaboo. 10 millipedes is 1 centipede, but I'm sorry, it looks more like a caterpillar. And 10 to the 6 aches is 1 megahertz. This is a bit cryptic. Here's a hint. In order to show when and how we need to convert to SI units, I've made a problem about a snail. It's probably a little bit easier than you might expect to find in an AP Physics exam, but it's just to teach about units. So, we've got this 150 gram snail and she walks across a garden at 1 millimeter per second. How far will she travel in 1 minute? Now we know speed is distance over time, and we rearrange it, and then we can just plug in the values. But why have I got the 60 seconds over 1 minute? In a sense, I'm just multiplying it by 1 over 1. So it's not changing the final answer, but I do that so that all the units cancel algebraically and leave us with 60 millimeters. Now, I think it would be fine to say 60 millimeters or 6 centimeters, but if in doubt, it's generally better to convert it to SI units and say 0.06 meters for the final answer. If you learn chemistry, you'll get used to working with units like this. It's a good idea for anyone, but it's not generally expected in physics, although I do recommend it as much as you can and have time for. So, how long will she take to reach her lettuce 2 meters away? Again, distance is 2 meters over 0.001, gives us 2,000 seconds. Although that is the SI unit, it's custom to convert an answer to something that we can kind of more easily visualize. And this also helps you as the student to figure out whether the answer is realistic. There's nothing more frustrating than grading a physics exam where a student gives a final walking speed greater than the speed of light and doesn't even realise something is wrong. So converting it to something more meaningful is a good way to check that it's realistic. Now, notice that in the first question we never converted to SI units. In the second one, I did convert it to SI units, but I didn't need to. However, once we talk about gravitational potential energy, then the formula for energy is mg delta y. G is given to us in meters per second squared, and mass must use SI units of kilograms. So here we must convert everything to kilograms and meters and just multiply that through, and it gives us 0.29 joules. As a kind of side note about the history and application of units, let's look at what's called the seconds pendulum. If we have a pendulum with a length that's very nearly 1 meter, it will have a period of 2 seconds, meaning it takes 1 second per swing. This has been very useful for clockmakers throughout history, and it can also be useful in the lab. If you don't have a timer with you or your phone's been confiscated or something, then if you just make a pendulum out of string that's basically 1 meter or 99.5 centimeters, then it will take 1 second to swing from one side to the other, as long as the swing isn't too big. However, a second is not defined as half a cycle of a pendulum with a length of 1 meter, and a meter is not defined as the length of a second's pendulum. My final slide here is really just for native speakers of East Asian languages such as Chinese, Japanese or Korean, or perhaps for students who grew up in these countries. In East Asia, people naturally think in terms of 4 zeros, while in the West we mostly think in terms of 3. Now 4 zeros is actually more logical because it allows for greater numbers to be understood and visualized more easily. However, because it goes back to the French Revolution, the metric system is very much based on 3 zeros, and converting between those two, especially under pressure in an exam, can actually be difficult or cause students to lose points. So, I suggest first converting between the two through a Singaporean way of thinking about it. Now, in Singapore, obviously it's heavily influenced by Chinese and British culture, and even native Chinese speakers there often think in terms of 3 zeros like English speakers. So instead of saying yuan, they say shiqian. So, for example, let's say you pull out this resistor and you figure out from its code that it's 10 to the 5 ohms. I suggest first converting that to Singapore style, ibai qian, or in Japanese, converts juman to hyakusen. From there, convert it to English, 100,000, and then finally you know the 1,000 is kilo, so it's 100 kilo ohms, and that would be your answer. Of course, you'd have to convert it back to SI units, 10 to the 5 ohms, if you're doing another calculation with it. Just a suggestion. Thanks for watching.